Hey, good morning everybody, and welcome back to Calc 3. Plan for today is I'm going to do some discussion about the courses the math department is going to be offering in the fall, because the course schedule came out today, and I just want to kind of give you my thoughts on what makes for sort of good follow-up courses for this class. Then we've got Standard 11 quiz, and then we will finish off Standard 12, finishing our discussion of local extrema. My next office hours are the usual ones on Monday in the hour before class and from 2 to 3. And as far as homework goes, I am planning on doing a Standard 12 quiz on Monday. What do you call a mathematician who enjoys working on a farm? You call them a protractor. Okay. So if you haven't seen yet, the math department's list of courses has come out for next semester. Or did I say math department? The schedule of courses is out for the fall, and so I thought I would talk a little bit about what's coming up in terms of what my thoughts are on what you should take. I haven't listed the ones. There's a few I haven't listed. Like if you're in Calc 3, I'm assuming you're already taking Calc 1 and Calc 2, so I'm not going to list those, but just kind of the main ones that are kind of good follow-ups to this class. First of all, linear algebra. My opinion on linear algebra. If you have not taken it yet, you should. It is very important. Basically, anything you do in higher level math is going to involve some amount of linear algebra, including in this class, with stuff like this we're going to be doing today, with taking determinants and such. This is a good one if you're interested in doing a math minor or a math major. Kind of linear algebra and this class are sort of the two classes that are sort of your gateway to the rest of the major, including the upper level classes. So I think linear algebra is a great one to take. Prereqs, I'm just going to put a check mark under prereqs to basically just say you already have them. If you're taking this class now, you can take linear algebra. It's offered every semester. Let's see, it's offered 2 sections in the fall, 1 section every spring, so it is every semester. Non-Euclidean Geometry, on the other hand, is one that's only offered once every 2 years. And it's sort of a course that's sort of the more mathematically mature, the grown-up version of the Math 105 core course, in that we sort of take a look through both at Euclidean geometry, what did Euclid do, what was his importance, and talk a little bit more about the history of how did geometry and its study evolve beyond what Euclid did thousands of years ago, and what are kind of some of the more recent developments in geometry. Non-Euclidean, and that one only has a Calc 2 for you. Non-Euclidean Geometry, I think, is a great course if you're interested in like more pure theoretical math. It's a great course that I think will serve as like an intro to proofs type course if you're interested in the more pure side of the math major. Pure meaning theoretical, writing proofs and such, versus applied, which is more using math to solve real world problems. I think Non-Euclidean Geometry is sort of a great course to prepare you to take an upper level proofs course, like say a 400 level course like Abstract Algebra or Real Analysis. I think something like Non-Euclidean Geometry would be good under your belt for being ready to take one of these big, scary proof courses that right now don't believe require any prereqs in terms of proof writing courses, but will likely in the future. Probability, which has a prereq of this class and is offered every fall. Hey, Dr. Trelaw, you've taught this one and I haven't, so what are your thoughts on probability?
Applications of multivariable calculus. Yeah, just the idea, if you want to think about probabilistic things that aren't certainties in these sort of determinate systems, you just want to understand how you quantify uncertainty and try to make sense out of it. That's probability. Leads into statistics and some other statistical learning courses.
Yeah, I was going to say, if you have an interest in like statistics, especially like higher level, not just introductory level statistics, probability is a good one to take. That one's offered once every year in the fall. believe Dr. Schuller is offering 2 sections of it, and is one that is currently required for the applied math major. Next up is Discrete Math, which only has a Calc 2 prereq. Discrete Math is an interesting one, in that it sort of also fills that niche of being like an intro to proofs type course, in that it's going to involve a fair amount of proof writing, but also some computation and discussion of things. Right now, it is not a regularly offered course, even though we're currently discussing making it one in the future. But that's kind of still to be determined as we figure out how we want it to integrate with things like upper-level proof courses in computer science. Discrete Math, I think, is great if you're thinking more pure or applied. There's kind of like it's a nice combination of both. Of like kind of more theoretical proof writing and techniques, but also some applied things like being able to do a lot of like combinatoric type stuff, being able to learning how to count properly. Nobody knows how to count properly, but you will learn how to count better in this. It fills somewhat of the same role as Non-Euclidean Geometry in its intro to proof readiness, but Non-Euclidean Geometry, I would say, is a little bit more abstract, a little bit more theoretical in nature, whereas Discrete Math is going to be a bit more concrete. If you're thinking like you're on the more pure side of the major, Non-Euclidean or minor Non-Euclidean Geometry and Discrete Math are good. I think would both be good. Whereas if you have more of an applied interest using math to solve real-world problems, Discrete Math is definitely a stronger fit there. So next up is Numerical Analysis, which is sort of the 400-level proofy course that is required for the applied math major. This one does have a prereq of 310, so it's the first one, depending on what you've currently taken, you might not be ready to take this coming fall. It's offered every fall, and it's a course in sort of more... Dr. Trelaw, can you explain numerical analysis for me?
Finding solutions to anything other than nice linear equations is very, 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 very difficult. And so if you need to come up with approximations or methods for approximating solutions to systems of equations in particular, it gives you a lot of tools and techniques for doing that and understanding what you do and why you do it.
Yeah. Definitely has a reputation of probably a more challenging course, I'd say, than these top 4, but a decent amount of theory sprinkled in, as well as looking at and kind of analyzing a bunch of these different sort of computational approximation techniques. Abstract algebra. I've taught this. I'm not teaching it this fall, but I've taught it the last 2 years. It's my favorite. It's my area of research. This is abstract algebra, along with its springtime cousin, real analysis, is one of the 2 big, scary proof courses. That's one where I think it would benefit a lot from you taking something like non-Euclidean geometry or discrete math first. But it sort of looks at more discrete structures, like what do the set of all integers have in common with the set of all 2x2 matrices, for instance, and looks to kind of find connections and relationships between these different sort of more abstract mathematical structures. It's a lot of fun. I love it. It's terrorized a lot of students to come through. Abstract algebra is required for the pure math major, and for the applied math major, it's one of you either have to take it or real analysis, which is a more calculus-based, but also scary proof course. And that's also offered every fall. The last 2 are not listed with the other math courses, but they are going to kind of be housed within the math department. We actually just hired a computer scientist to come start teaching computer science at Hillsdale this fall. And he's going to be teaching 2 computer science classes, Intro to Programming and a course in Artificial Intelligence. I think both of which you should be able to get into with what you have. Honestly, take Intro to Programming. It's the sort of course where he's not going to assume you have any sort of background in programming necessarily, other than you've seen a little bit of mathematical ideas and structures. But Intro to Programming is a great course. I think it's a hugely important skill in any of the sciences, and honestly in a ton of different disciplines, being able to know how to interpret, how to write some programs, and how to use them to complete text, just because computers are so useful and so ubiquitous in modern society. You should take this. And I believe the plan is going to be to offer this every semester from starting this fall. Is that right?
Yeah, there's 2 sections this fall, and then in theory, if there's interest, it'd be offered every semester.
Sure. Sarah.
Will either of these classes count towards, say, math minor or math major?
Good question. So these top 1, 2, 3, 4, 5, 6 classes are all count towards a math minor, math major. The bottom 2 are going to count towards computer science minor, which is going to be, fingers crossed, if everything goes well, starting up this fall. We might be a computer science major in the future. That's a little bit iffy. Is this going to count towards, say, like an applied math major? That's something our department's currently in discussions about. I will say this, out of the top courses, Discrete Math, the plan is to have Discrete Math actually be able to count for for all of the above, for the computer science minor or an applied or pure math minor or major. So Discrete Math kind of counts for everything. The others, the ones with the MTH, just count from the minor and major. Dr. Chalor has something he would like to say.
Yeah, I just want to point out, whether or not students sometimes don't know this until their junior or senior year, there's no double dipping. Like, you cannot count the same course towards a major and a different minor. So when Dr. Gerstel says that Discrete Math could count towards math or applied math or computer science, it really is an or. You can't
it's
have
an
it count
XOR.
towards.
You can only have it count towards one of those things, and not like you can't apply this. You can't take Discrete Math and have it count towards both a computer science minor course and towards like a math minor or a math major course.
So I won't actually be around next semester, but I'm still.
How unfortunate for you.
Yeah. What language is Intro to Programming?
He's planning on Python, right? So for the intro course, he's planning on having it mainly be done in Python. And someone else said it. No?
I guess this is kind of a question for is your probability classes
Is what?
R?
Yes. Sometimes, and it'll probably have a little bit more this fall than it did last fall. But yes, it'll involve it to some degree.
And sort of the last course I wanted to advertise is a course on artificial intelligence, which in the future, the plan is, I think, to have it have an intro to programming prereq, but since intro to programming is kind of being officially taught for the first time this fall, it will not for this fall. I think it only has like a Calc 1 prereq. And so this would be sort of a course that's would also count towards a computer science minor, definitely one if you have any sort of interest in sort of artificial intelligence, machine learning. Dr. Chalor, how does artificial intelligence as a class mesh with statistical learning?
It's so we do offer a 425 course. We've offered it every other spring for a couple of years now, which is statistical learning, and it's the math side of machine learning, of prediction algorithms and things like that. My understanding is the AI course is going to be more of the computer side of machine learning and artificial intelligence. So in both of them, you'll talk, I think, a bit about some math. In the statistical learning, you also implement things usually using R, the different algorithms. But this one, the AI will be a little bit more computer science-y, focusing on that implementation, and the statistical learning will be more math.
And the plan for artificial AI to be offered like every 2 years?
Every other year, yes. My best guess is that it'll be offered again 5 semesters after, in a fall semester, but in a year and a half.
Fall of like 23?
Yeah, something like that.
Okay. Yeah, so I will say, some of these courses do not have official descriptions in the catalog yet, namely the 2 computer science courses and Discrete Math, since that is currently being offered as a topics course. The rest of these have descriptions in the course catalog that you can read. For Discrete Math, if you haven't figured it out yet, I'm going to be teaching that one. And I actually have there's actually a couple of posters, one on my office door and one kind of in the bulletin board in the first floor of Dow Science, if you want to kind of get a better sense of what that one's going to be about. Yes?
So now for those last two, the computer science ones, are those 3 credit classes?
Yes. Yes, I think all of these are 3 credits. These are all, the only 4 credit classes in the departments are basically the calc sequence. So everything from in this list is 3 credits. Most of which, I think other than linear algebra, I think most of which are going to be taught as Monday, Wednesday, Friday courses. Are there questions or comments on any of these? If you have any more questions about any of these, I'd be happy to talk to you more outside of class. Send me an email or come by my office hours. If you're unsure if if a particular course is right for you, be happy to give you more thoughts on that. Okay, and with that, it is quiz time. So as per usual, about 10 minutes to work on this, and if you have any. Hey, Dr. Fuller, do you want a quiz?
Variable calculus.
I put one in there for you. All right. I'm going to write a few things on the board, but it's irrelevant. Don't worry about it while you're taking the quiz. It's just to save some time after the quiz is over. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes forward, please. Okay, so for the rest of the class, we're going to finish up our discussion of Standard 12, which we started on Monday. Standard 12 was our discussion on local extrema. So you may remember that on Monday, we kind of did a little bit of review of Calc 1, talking about how do we find local max, local min, what do these terms mean. We worked through an example where we found our critical points, used the second derivative test on a Calc 1 function to determine whether we have a local max or a local min. And we also kind of talked through and looked at a few pictures, or a few graphs of Calc 3 examples. Right, in Calc 3, we're going to be looking at functions going from Rn to R here. And we said that f is going to have a critical point at A if f of A exists, so if the point A has to be in the domain of your function f, and it has to be the case that either f is not differentiable at A, or that the derivative consists entirely of zeros, meaning all the partial derivatives of f, when you plug in that point A, if A is a critical point, it's going to give you 0 in each case. And we said that f is going to have a local maximum at A if f of A is greater than or equal to f of x for all x that are near A. So something like a downward shaping bowl here. If you look at my finger at this top knuckle here, that's going to be a local maximum of a three-dimensional graph because the height at this point, the z-coordinate output, is going to be greater than the z-coordinate output of all the points nearby. Whereas if I point it downward, this is now going to give us a local minimum because the height at this point is going to be smaller than or more negative than the height at all of the nearby points on my finger, so to speak. And we discussed a brief theorem, which says, just like the Calc 1 version, if that you have a continuous function f that happens to have a local maximum or a local minimum at a point A, then f has to have a critical point. Anytime a local max or a local min occurs, you have to have a critical point, meaning a point that's in the domain and your function is either not differentiable there or the derivative matrix consists entirely of zeros. So you might remember what we said about kind of the vice versa of this. If you have a local max or a min, that has to occur at a critical point. But do all critical points have to have maxes or mins? Or is it possible for a multivariable function to have a critical point that's neither a local maximum nor a local minimum? Turns out we actually did have a special name for a critical point that's neither a max nor a min, which we saw when we looked at f of xy equals 1/2 x squared minus y squared last week. That function sort of had this point here where it was a maximum in one direction along the x direction and a minimum in the other direction, in the y direction. Does anybody remember what we called this type of point, where it was a critical point, but neither a max nor a min because it was maximizing and minimizing in different directions? Right?
Saddle point.
Bingo! Yeah, we called this a saddle point, which as a reminder is just a critical point that is neither a local max nor a min. So anytime you have a max or min, it has to occur at one of these critical points, but it is possible to have a critical point that's neither a local maximum nor local. And so today's class, we're going to come up with sort of an algebraic way of being able to tell, even if we can't necessarily look at the graph of a function, how can we tell if a critical point is the location of a max, of a min, or of a saddle point? And to do that, we're going to have to use the multivariable version of the second derivative test. So we talked a little bit about on Monday about what the Calc 1 version said of the second derivative test. It basically said if you have a critical point like this, where f prime of a is equal to 0 and f double prime of a is positive, then that's going to give us a local minimum. And the Calc 1 version said that if you have a critical point like this, where f prime of a is 0 and f double prime of a is negative, that's going to give us a local maximum. But it's going to be a little bit harder for multivariable functions because we can't just say take f double prime at a point. What's the problem? When we're looking at a multivariable function, a function that's taking in vectors and Rn as inputs, why can't we not just say for something like f of xy equals x squared minus y squared, why can't we just say f double prime of, I don't know, 1, 2?
It can be different depending on the direction.
Yeah, that's exactly right. In Calc 1, it's okay to just say f double prime because the second derivative only has one value. But in Calc 3, we have second order partial derivatives, which we talked about a few weeks ago. Like we could take something like f sub xy, where we differentiated with respect to x and then with respect to y, versus something like f sub y, which is just we differentiate with respect to y twice. In other words, a multivariable function can sort of have multiple second derivatives going on, in that it has different second order partial derivatives. And does anybody remember our Revolutionary War name for the matrix that contains all of these second order partial derivatives? What?
Isn't the Hessian?
It is, the Hessian Matrix. And so, the multivariable version of the second derivative test is not just going to be take a look at a single number and see if it's positive or negative, like the Calc 1 version. Instead, we're going to have to look at the Hessian Matrix and look at how different properties of the Hessian Matrix can tell us whether a critical point we find is a max, a min, or a saddle point. So let's write this one down. So this one's in the packet. If you don't want to write this one down yourself, this one, it is a bit lengthy. But the idea is we're going to be looking at the Hessian matrix, and we're going to be taking determinants of the Hessian matrix to tell us if a critical point, what type of extremum it is. So this is the second derivative test, Calc 3 version. And the idea is we're going to suppose that we have a function f from Rn to R that is C2, meaning all of its second order partial derivatives exist and are continuous everywhere. And I forgot to include this in the packet, so you might want to pencil this in. We're going to suppose that f is C2 and that A is a critical point of f, meaning a point that's in the domain of f where the derivative is entirely zero, all the partials are zero, or f is not differentiable there. And then the Hessian matrix was this matrix of our first order partial derivatives, fx1, x1, fx2, x1, all the way down to fxn, x1, evaluated at a, fx1, x2, up to fx1, xn of a, and this will be fxn, xn of a. So this was the Hessian matrix of the function f evaluated at a. And if A is a critical point, then properties of this matrix are going to tell us what type of critical point it is. Specifically, what we're going to end up having to do is to take determinants of essentially what's the top left corner of this matrix. We're going to take the determinant of just the matrix by taking just the top left piece. We're going to take the top 2 by 2 piece, and eventually we're going to be working our way up to finding the determinant of the entire matrix. And by looking at all these different determinants, we can say max, min, saddle point. And this process is going to be called taking the sequence of principal minors. Of HF of A. And that's just going to be the sequence of the following terms. To start, we're going to write D1, and that's just going to refer to the top left entry of the Hessian matrix. What happens if you differentiate twice with respect to the first variable? fx1, x1, and A. D2 is going to be what happens if we take the top left 2 by 2 matrix, so kind of the top left, the top 2 rows, leftmost 2 columns, those 4 entries, and we take the determinant of what we get when we take that expression. I'm putting vertical bars here because it's not just that 2 by 2 matrix, it's the determinant of that matrix. And we're going to keep doing this. D3 means taking the determinant of the top left 3 by 3 kind of submatrix within the Hessian matrix. And we're going to keep doing this all the way up until we get to Dn, which is going to be the determinant of the entire Hessian matrix. So if you have a function from Rn to R, you end up with n of these. So if f is going from R3 to R, you'll have a D1, D2, D3, for instance. And what's going to happen is if all of these terms, these principal minors, come out to be positive, then f is going to have a local minimum. So if dk is positive, by the way, anytime I see dk, I always think of Donkey Kong, because I grew up playing a lot of video games. So if you want to think about gorillas doing this process, be my guest. If dk is positive, for all k going from 1 up to n, then f has a local minimum at a. If the top left entry, the determinant of the top 2 by 2, the determinant of the top left 3 by 3, all the way up to the determinant of the entire Hessian matrix come out to something positive, we're going to have a local minimum. Second, for a local maximum, you might think, oh, the local maximum is going to happen if all of these terms are negative. Turns out that's not the case. In order to have a local maximum, it turns out that D1, D2, D3, all the way up to Dn have to alternate in sign. Meaning, if dk is negative for all odd values of k, and dk is positive for all even values of k, then f has a local maximum at a. So the third part is going to be what happens if neither of these occur. Well, if neither of these occur, then typically you're going to end up with a saddle point. And so if neither of the top two cases occur, and if Dn, the last one, the determinant of the entire Hessian matrix, is non-zero, then f has a saddle point at a. And finally, we can say if Dn is equal to 0, meaning the determinant of the whole Hessian matrix turns out to be 0, then just like the Calc 1 second derivative test, the Calc 3 second derivative test is going to fail, meaning it's not going to tell us any information. Specifically, then we would say A is a degenerate point of f, and the test fails. Meaning the test doesn't tell us any useful information about whether A is going to be the location of a local maximum, a local minimum, or a saddle point. That's a big theorem. I dare say this is probably the longest theorem statement we might see all semester, in terms of just how much stuff is going on. It really is generalizing this idea, though, of the Calc 1 second derivative test, in that if you know how all your second derivatives behave, in this case the second order partial derivatives behave, you can use that to determine local maxness or local minness. The key difference, though, is that in Calc 1, you just have f double prime of A as just a single number, whereas here, you get an entire matrix of values when you evaluate all your second order partial derivatives, And so you have to kind of look at these different minors, these different determinants of submatrices of the Hessian matrix in order to be able to tell, is it a local min, a local max, or a saddle point. So Dr. Gerster, I can get on board with number 1 here. All these dk are positive, local min, sure, makes sense. Why is it the case that for local maximum it has to alternate? There's actually like a very kind of big question relating to the theory of something called quadratic forms being positive or negative definite. I'm going to not go through all of the details of kind of where do these different terms come from, how do we know that this theorem is true. The book does go into a lot of detail on this matter, but I'm less interested that you know why this theorem works and more interested in seeing, do you know how to go through and actually apply this theorem? Because unfortunately, there's not like a 5-second quick explanation I can really give as to why property number 2 works out the way it does. But any questions before we move on to looking at an example? Yes, Emily?
What is the determinant of the principal minus polynomial about the graph?
Sure. So what does this tell us about the graph itself? It kind of depends based on the individual minors. So like the first one just says slope in the x direction. It basically just says concavity in the x direction. If this is like a function of like f of xy equals blah, this one is just telling you what's the concavity in the x direction. The others are a little bit trickier and hard to give like an exact thing saying, oh, it clearly refers to the slope in this direction or the concavity in that direction. It's sort of giving us information about how do all the different slopes and concavities in different directions sort of intertwine with each other, I guess is the word. If you wrote this out, it's the derivative, the concavity in the x direction times the concavity in the y direction minus this term squared, because if f is C2, these should be equal to each other. And for D2 and up, it's hard to give an exact, like, clear mental image of, oh, this is what this determinant is referring to. We had like another like 2 classes to go into like a big tangent on like trying to derive where do all of these things come from. We can sort of get a little bit of a sense of, okay, I can see how this maybe gives some geometric information, but there's not like a quick and easy answer to that question, unfortunately. It's a good question. I don't want to just throw you under the bus and say, yeah, it's stupid. I don't want to talk about that. It's just, I have to kind of pick and choose how we want to spend our time. Yeah. So to speak. Any other questions about the statement of the theorem? So now we're going to apply this theorem by looking at an example where we're going to take a function, f. We're actually going to take one going from R3 to R, and we're going to actually go through and see how we can use this theorem in order to tell us something about our critical points. And if you're on the next page in the packet, the function I want to look at is f of xyz is equal to x cubed plus xy squared plus x squared plus y squared plus 3z squared. And our goal is going to be find all the different types of extrema. Find and classify where are our local mins, where are our local maxes, where are our saddle points for this particular function. So this is a function from R3 to R, not R2 to R, so I can't pull up Calcplot 3D and give us a nice graph of what does this one look like. So we wanted to start by just finding where are our maxes and mins. What do you think would be a good first step? Something that we could do right off the bat that'll put us on the path towards finding critical points or maxes or mins. Laurie?
Finding the first derivative.
Okay, let's differentiate it. Sounds pretty useful. So, first derivative is going to be made up of del f del x, del f del y, and del f del z. which, let's see, del f del x is going to be 3x squared plus y squared plus 2x. Del f del y, I'm putting this bar here just to kind of distinguish. This one's del f del x, and what comes next is del f del y. Del f del y, 2xy plus 2y, and then del f del z is just going to be 6z. Neato burrito, we have ourselves a derivative. Lori, what did you want to do with the derivative? Oh, you want to go right to finding the Hessian matrix? Yeah, we can certainly do that. I don't want to find I kind of don't want to find the Hessian matrix quite yet. If you look at the statement of the second derivative test theorem, before we do anything with finding the sequence of principal minors and looking at properties of the Hessian matrix, we need to know something else first about this function f that just relates to how does the first derivative, properties of the first derivative. So specifically, there's something I'd like to do with the derivative matrix that we get here that's going to tell us about the potential points where we could find local maxes, local mins, and saddle points. Luke?
You want to see where each of the partial derivatives are equal to 0?
So you want to set this equal to the 0 matrix, and what's that going to give us?
It will then give us variables where
So they're going to give us potential locations of maxes and mins. And what do we call those points where we could potentially have a max or a min, or otherwise a saddle point? Rob?
Critical points.
Yeah, let's find our critical points, which I agree we can do by finding where is the derivative matrix just 0, and also potentially where is the derivative undefined. So that's going to be our first major step here, is we're going to find the critical points of f. So first of all, are there going to be any points, anything we could plug in for x, y, and z that's going to make our derivative undefined? Or is anything in R3 going to be okay to plug in for x, y, and z here?
Yeah, they're all polynomials.
Yeah. These are all polynomials. They're going to be defined and continuous everywhere. So we don't need to worry, in this problem at least, about the derivative failing to exist at a point. So I think we can just do what Luke suggested earlier. The only critical points are going to be wherever the derivatives, all of our partial derivatives, are going to be equal to 0. So since f is differentiable everywhere in R3, the only critical points occur when the derivative matrix is just going to come out to zeros. So if we set the derivative matrix equal to the matrix of just 3 zeros here, we're going to end up with 3 different equations. We're going to need, if del f del x is 0, that's going to tell us that 3x squared plus y squared plus 2x is equal to 0. If del f del y is 0, then 2xy plus 2y is going to be equal to 0. And finally, if del f del z comes out to 0, that's going to tell us that 6z has to be equal to 0. And so our goal in finding critical points is going to be, what are our values for x, y, and z that's going to make all of these equations true? In other words, if we try and solve this system of equations, what can we plug in for x, y, and z that'll make all of them true, which will in turn cause the derivative matrix to come out to just be all zeros, which, as Luke said, will then give us our critical points. So right away, I look at this system of equations, and two of them look kind of scary, but one of them looks pretty easy to solve for a variable. Yeah, I see you kind of nodding along. So which equation do you think we could solve very quickly to tell us some useful information?
6z equals 0 shows us that any critical point will have a 0 for the z value.
Yeah, exactly. I mean, we could 6z equals 0 right away is going to tell us that z has to be equal to 0, which means exactly what Brianna just said. Any critical point for this function is going to have a z coordinate equal to 0. Top two equations, though, look a little bit scarier. I want to focus next on the second equation, because the top equation, I don't know how to deal with that. It involves squaring things, and gosh, that's not even a linear equation. Second equation's not so bad. If 0 is equal to 2xy plus 2y, what's another way that we can rewrite the expression 2xy plus 2y in a way that'll make it a little bit easier to tell us something about x and or y? Avery? Okay, so you factored the 2xy plus 2y to get 2y times x plus 1. Seems pretty reasonable to me. Sarah, if we knew that 2y times x plus 1 was equal to 0, what does that tell us about x and or y?
That one of those basically like the parenthetical expression, either x is equal to -1 or y is equal to 1.
Yeah, I like it. We're taking two terms, 2y and x plus 1, and multiplying them together to give us 0. That means one of those two terms, at least one of those two terms, has to be equal to 0 itself. So this is going to tell us either y is equal to 0 or x has to be equal to -1 to make this work. Or potentially both. If x is -1 and y is 0, then this expression is doubly going to equal 0. So, second equation is also going to tell us some nice information about our critical points. Third equation told us the z-coordinate of any critical point has to equal 0. Second equation told us, given any critical point, either its y-coordinate is 0 or its x-coordinate is -1. So, how can we maybe use this information from the second equation, the fact that y equals 0 or x equals -1, how can we maybe try and find some information now using that fact with the first equation, the del f del x equaling 0 equation? This one's a bit tricky. But something I think we can try to do with this top equation is, if we know y has to equal 0 or x has to equal -1 in order to have a critical point, we could just try plugging in y equals 0 into the top equation and seeing what would x have to be. Or we could try plugging in x equals -1 into the top equation and see what would y have to be. So let's try that out. Keep these partial derivatives because we'll need them here in a minute. So we can say if y is equal to 0, the top equation is going to tell us that 3x squared plus 0 squared plus 2x is going to be equal to 0, which is the same as saying 0 is equal to 3x squared plus 2x. And that's an equation I think we should be able to solve. Let's see. Holly, put your hand up earlier. If if we wanted to find the values of x that would make 3x squared plus 2x equal to 0, what could we try and do?
We factor out of x, so that means x minus parentheses 3x plus 2, and we set that equal to 0. So like x equals 0.
Sounds good to me. Yeah. We get that x times 3x plus 2 is equal to 0, which tells us x equals 0, or 3x plus 2 is equal to 0, which if we solve that for x, I think we get x is equal to negative 2/3. So what we just found is that if z is equal to 0, and y is equal to 0, and x is either 0 or negative 2/3, all three of these equations are going to be satisfied. So I think that's then going to tell us, in other words, that that's going to give us two different critical points. We're going to get a critical point when x is 0, when y is 0, and when z is 0. We're also going to get a critical point when x is negative 2/3, y is 0, and z is 0. Because we're still operating under this if y is equal to 0 scenario. Alex? Oh, what happened to that? We didn't use it. So we should probably address that. I think would be a good idea. So right now I think what we were doing is splitting this up into two cases. Saying, well, if the second equation works, it holds true, then y has to be 0 or if x equals negative 1. We found two different scenarios where if y equals 0, that we get a critical point. But I think we should also check, Max, I think I agree with you, we should also check if x equals negative 1. That's another way to make the second equation hold true. Are there some other critical points we could get by trying to plug x equals negative 1 into the top equation? Because potentially that could give us some more critical points. So let's take a look at that. Is everyone alright if I erase the if y equals 0 piece? So the other thing we need to check is if x equals negative 1, is there anything we can plug in for y that would make the top equation hold true? Well, what we would end up with is 3 times negative 1 squared plus y squared plus 2 times negative 1 would have to be equal to 0. 3 times negative 1 squared is just 3, plus 2 times negative 1 is negative 2, so 3 minus 2 is 1. We would get y squared plus 1 is equal to 0. And what values of y would solve the equation y squared plus 1 is equal to 0? Huh? No value of y. Gadzooks. Y squared, no matter what y is, y squared plus 1 will always be positive. There's no solution here. And so what ends up happening is if x is equal to negative 1, then this second equation is satisfied. Out of the three equations, we need to hold true to have a critical point. But if x equals negative 1, we just showed it's impossible for the first equation to be satisfied as well. So it turns out, Alex, to kind of answer your question, turns out we don't get any new critical points from setting x equal to negative 1 and looking at the first equation. But it was important to check that, because if we were able to solve this for y, like let's say it had come out to y squared minus 1 equals 0, that would have given us new critical points that we would have had to check for local max and minness later on. So it turns out these are our only two critical points. We have a critical point at the origin, 0, 0, 0, and another critical point at negative 2/3, comma 0, comma 0. Those are the only 2 points in R3 that will simultaneously make all 3 of these equations hold true. In other words, that would make the entire derivative matrix equal to the zero matrix. By the way, side plug. With Dr. Gerstel, why can't we plug in y equals I into that equation? Well, if you want to do calculus with imaginary numbers, I'm going to be offering a complex analysis class this summer, in the first summer session, where we're basically going to be doing like Calc 1, Calc 2, and Calc 3, but using imaginary numbers. And we're going to be getting into all sorts of mischief, being able to look at and kind of see a lot of cool facts about that. So if you want to take complex analysis and see how do imaginary numbers play into all this, sign up for my course. Or you could sign up for Dr. Treloar's game theory or something too, I guess. So that was just step, oh gosh, low on time. So that was just step 1. And the next step's going to take us at least 5 minutes. I don't want to hold you. I tell you what, change of plan. Standard 12 quiz is now postponed to Wednesday, just so we have the time to go through the rest of this problem. Because we still have to do what Laura suggested, take the Hessian Matrix, plug in our critical points, see whether they came out to local maxes or min. So, in class on Monday, we'll finish off this example to kind of finish standard 12, and then we'll also start standard 13, where we'll be looking for absolute maxes and absolute mins of functions. Meantime, hope y'all have a good weekend. I will see y'all on Monday.